Hello class 12. The topic that we're going to discuss today is matter waves. Now, before we talk about matter waves, let us discuss about a photon, or so to say, let us discuss about light. Now, we've already discussed topics like photoelectric effect, which proved that light is a particle, light behaves as a particle. It was proven by using quantum theory given by Planck. Planck's quantum theory was used by Einstein to explain photoelectric effect. So it proved that light is a particle, light behaves as a particle. And there are other, phenomena also like black body radiation and Compton scattering, which proves that light is a particle. And of course, we've studied about topics like interference and diffraction, which proves that light is a wave. Okay. Also, there is something called polarization of light, which actually proves that light is a transverse wave. That topic has been removed from your syllabus only for this term. All right, but do remember, phenomena like interference, diffraction, and polarization, they prove that light is a particle. Light behaves as a wave. And phenomena like photoelectric effect, Compton scattering, black body radiation, these are phenomena which proves that light is a particle. So to say, light has dual nature. It sometimes behaves as waves and sometimes behaves as particle. Alright. Now, from Einstein's energy mass relation, the energy of a photon, so to say, is given by E is equal to mc squared. So, where m, by the way, is the kinetic mass of the photon. A photon is never at rest. Okay, it is always moving. So m is the kinetic mass, whereas the rest mass of a photon, since a photon is never at rest, the rest mass of a photon is 0. So m is the kinetic mass, mind you. So the kinetic mass of the photon m can be written as E by c squared. So this is equation number 1. Also from quantum theory, Planck's quantum theory, the energy of a photon is given by E, which is h nu, where h of course is a Planck's constant, having value how much? H is 6.626 into 10 to the power minus 34 joule second. So H is a Planck's constant and nu is the frequency of the photon or frequency of light. So substituting for energy from equation 2 in equation 1, we get to see that mass of the photon, the kinetic mass of the photon is h nu by c squared, and thereby the momentum of the photon given by P, which is equal to mass times its velocity, is given by h nu by lambda, which can also be written as h by lambda, since velocity is frequency into wavelength. So remember, the momentum of the photon is given by h by lambda. So this is the momentum of a photon or light, so to say, which sometimes behaves as a particle and sometimes as wave. Now comes de Broglie, someone by the name de Broglie, a French physicist de Broglie, who gave actually a bold hypothesis at that point of time, somewhere in 1920s. Okay, so he said, why only photons? Why only it's photons that sometimes behaves as particles and sometimes as waves? Okay, and he said, anything that is moving, any body that is moving, any particle that is moving, which has a certain mass of course, if it is moving, then it behaves as a wave. That is the hypothesis he gives. Okay, so that is the hypothesis he gave, and he said that not just photons, but any moving body, any moving particle will have a wavelength lambda, since it is behaving as a wave according to de Broglie. Okay, and the relationship between the wavelength and the momentum, or so to say, he said the wavelength of that moving body is given by h by p. He used the same expression which is true for a photon actually. So for a photon, the wavelength of the photon is given by h divided by its momentum. So he said exactly the same thing. He said any moving body has or behaves as a wave whose wavelength is given by lambda, which is h by p. And this lambda is called de Broglie wavelength of that moving body, of that moving particle. So that is exactly what matter wave is all about. Any matter, any body that is moving also behaves as a wave according to de Broglie, okay, and the wavelength of the matter wave is given by lambda, which is equal to h by p. He used the same expression actually, like I've already told, that is true for a photon. So this is your de Broglie wavelength for matter waves. Now, de Broglie hypothesis was proven to be true when two physicists by the name Davison and Germer, they performed an experiment, and they showed in the experiment that electron could be diffracted. Electron, which is a particle, it undergoes diffraction. Now, diffraction in itself being a phenomenon which is exhibited by waves. Now, Davison and Germer, therefore, in their experiment, they showed that electrons, which are particle, it could be diffracted, okay, and thereby the name of the experiment, Davison and Germer experiment. So in this experiment, it is shown that electrons, which are particles, also behaves as waves, and thereby hypothesis given by de Broglie was demonstrated to be true. So sometimes you will be asked, name one, experiment or phenomenon which proves de Broglie's hypothesis. So you will have to write Davison and Germer experiment on electron diffraction. If you write on electron diffraction, it will be more precise. Okay, so since electron could be shown to exhibit wave properties from de Broglie's Davison and Germer experiment. So let us now try calculating the de Broglie wavelength for an electron. Now we already know de Broglie wavelength is given by h by p. For any body this is true, for any moving body. So which is equal to h by mv, where m is the mass of the body, v is the velocity of the body. Now we also know kinetic energy is given by half mv squared. From here we get to see the velocity of the moving body is square root of 2k by m, where k is the kinetic energy, don't forget. So substituting this value, we get to see that the de Broglie wavelength for any moving particle, this expression is true for any moving particle. So de Broglie wavelength for any moving particle is h by square root of 2mk. You can check the mathematics yourself, verify the mathematics yourself. So this thing inside the box is, like I said, the de Broglie wavelength for any moving particle, also true for an electron. Now, in case of an electron, we have an electron which is accelerated, say in a discharge tube, through a potential difference V. Okay, then the kinetic energy of the electron is given by E into V, electron volt, remember. So E into V. So substituting for K, this is specifically in case of an electron, remember. This is true for any general body. So specifically in case of the electron, the kinetic energy is given by E into V, and thereby the de Broglie wavelength for an electron is given by lambda, which is equal to h by square root of 2m eV. So this is the expression for the kinetic energy, the de Broglie wavelength of an electron. Now you can see in this expression, h is a constant, m, the mass of an electron in this case, the mass of an electron is a constant, E is a constant, the charge of an electron is a constant. Alright, so when you substitute the values for these constants, so you get to see lambda is, how much is h? Planck's constant, 6.626 into 10 to the power minus 34 joule second. You substitute the value. M, the mass of the electron is 9.1 into 10 to the power minus 31 kilogram. E is 1.6 into 10 to the power minus 19 coulomb. So when you substitute the value, this and work out the mathematics, you can try that out yourself. You will get this to be 12.27 into 10 to the power minus 10 meters divided by square root of V. So V is the only variable, so to say. All the others are constants over here. And this can also be written as 12.27 angstrom, because 10 to the power minus 10 meters is 1 angstrom. So 12.27 angstrom divided by square root of V. So that is the value of de Broglie wavelength for an electron. So with this, we come to the end of matter waves. Thank you.